Okay, so today the idea was to give you mostly some other properties related to the matrix multiplication. And then depending on how much time we have left, we can talk about systems of equations, which is one of the big things in linear algebra, like solving systems of equations. But yeah, where I wanted to start with was like just talking a little bit more about multiplication. So so this is like some things to keep in mind. So in the uh well, the thing is like the quiz it's through Respondos. So Respondos uses a lockdown browser, so actually it locks you out of everything else. So I mean, if you have any problems like with the Respondos, then you can just email me that you're having issues. But I don't think it's possible to. You would have to email me from your phone or something like that, I guess. I don't think it's possible for you to stay on the Zoom meeting because like Respondos should should not allow you to access any other windows on your or browsers on your computer. No, it's close notes. Yeah. You should also, I mean, not that I mind too much, but for the quizzes, but just because in the exam I will ask you to write it on paper, you should try to write it on paper um, as well during like the last 30 minutes of class. No, like around what, 9:30? Um, yeah, like once I said like what I needed to say, I'll uh, probably start the quiz, but it should be around 9:30 typically. So so yeah, so the first thing, which is like the most important thing about matrices is that if you have two matrices, if you have two matrices, A and B, then AB may not equal BA, right? I mean, we have done like a lot of examples about this in, yesterday. So, but this is kind of like the most important thing of the matrix multiplication. It's kind of what makes it more interesting than other operations you have studied before, that the order does matter. Yeah, no, you should write the solutions on paper. Yeah. I mean, like for the quiz, I mean, yeah, you should write everything down. Yeah, yeah. Um, so when this happens, when the product equals, since it's such a special case, it like it receives a name, a specific name. So you say that the matrix is commute when the order does agree. Okay, so again, like since multiplication, it's not always true that they will the multiplication will be the same in either order. In cases that that happens, that gets a special name, and you just call them matrices which commute or commutative matrices. Okay. Let me see. There was this problem.
Excuse me.
Yes.
So like, can you go to like math 250 the problem 19 because I'm sorry. I need some examples to demonstrate.
Yeah, that's the one I was going to do. So like yeah, like in the PDF I had given you this problem 19, which is like which was set find all the matrices all the matrices. And let's put it like 2 by 2 matrix. Well, I mean, yeah, all the matrices which commute with 1, 1, 1, 1. So, what you can do in this case is you call you're trying to find all the matrices for which the multiplication is doesn't matter, like the order when you multiply it with the matrix 1, 1, 1, 1. So what you want is like that A, B, C, D times 1, 1, 1, 1 should be the same as 1, 1, 1, 1 times A, B, C, D. So we're trying to find all the matrices for which this happens. Is that making sense?
Yeah, that makes sense.
And then you just like do, like what you do is each product individually. So remember, how do you multiply two matrices? You do this row with this column, you do the dot product of that. So if you do that, you get A plus B. Then you do this row with this column and goes here. So it gives you C plus D. Then this row with this column, it also gives you A plus B. And then you do this row with this column, it gives you C plus D. Okay. And then you do the same for the other one. So remember, it's always like the same convention. So now it's this row with this column, and now you give something slightly different, which is A plus C, right? And then you do this row. Well, you can do it however you prefer. This row with this column, you also get A plus C. And then you do this row with this column, you get B plus C. And then you do, well, yeah, this row with this column, and then you get B plus C as well. Okay, so notice that they're not exactly the same things like you get on either side, right? Like the entries look slightly different. Is that okay? So far, so good. But that gives you, like, what does it mean for two matrices to be equal? It means that every corresponding entry is equal to one another. So for example, this equation, the first entry tells you that like A plus B equals A plus C, right? The second entry tells you that A plus B equals B plus C. And then there's some repetitions. Like in fact, like some of the equations are kind of saying the same thing, but I'm still going to write them. Then this you get a C plus D equals A plus C. And then you get what? You get that C plus D equals P plus D. Is that making sense?
Yeah, it makes sense.
And then this gives you, it's actually what we will call later the system of equations. This is actually, we're solving a system of equations without using maybe a lot of that phrase, but well, now it's kind of fairly simple to solve the system because there's like an A and an A here. So that forces B to be C equal to C, right? So that gives you that one. Then what can you cancel here? B with B. So now you get that this one gives you that A equals D. And then what, do you get anything new here? No, if you do this one, you get that A equals D again, right? So it's repeated. I mean, you can put it if you want here, gives you the same information. And the last one, you can cancel the D's, and so you get the D equals B, which was also something that we had found before, right? So you only get like, kind of like of the four equations, two are kind of repeated. So you only get two important pieces of data. So if you had a matrix, so the matrix A, B, C, D, right? What this is saying is that, well, we can leave A and B as they are, but now we can substitute C with B and D with A, right? So what that's saying is that every matrix, so what this is saying is that every matrix where like the third entry equals the second entry and the fourth entry equals the first entry will commute with the original matrix. So here, like, there are no more conditions on the values of A and B. So here, like, for any values of A and B of A, B, this matrix will commute with, this will commute with 1, 1, 1, 1. Is that making sense?
Yeah.
So it's kind of fun. Isn't too yeah, you could also, if you prefer, you can leave it in terms of C and D, correct? Yes. Yeah, I mean, you just, like, the important thing is that you started with 4 variables, 2 kind of go away, and then you just keep 2 of the 4, right? I guess usually people prefer to keep the alphabetic, like, kind of going alphabetically. Maybe you prefer to keep the first 2 in the alphabet, but yeah, like, you could also have left everything in terms of C and D, or like A and C, or like, as long as you use all, like, the information from the equations to substitute it, it doesn't matter which of the variables you want to leave in the end. Is that making sense? So yeah, so there are, like, I mean, there are a couple of ways where in how you could write this answer. But as long as you did it correctly, they are all like equivalent, like represent the same solution to the problem. Okay. But you see, like, already for like an example like this, like already for a matrix like this, like which is relatively simple. Oops. Not every 2x2 matrix will commute with this one. It has to have like a specific form, you see. And so if you had changed the matrix, obviously, like the equations you would have needed to solve are different, and etc. So like it is very sensitive to the matrix you are given. Okay.
Okay.
So that's the first thing I wanted to say. Here are like other things that are fun to keep in mind on. So the first one again was that it's not always true that AB equals BA. So that's important to say. The second one is that okay, I haven't said it, but there's this thing called the zero matrix. Well, it's kind of like kind of what you would expect it to be. So the 0 2x2 matrix is 0 0 0 0. The 0 like 2x3 matrix is like what, 0 0 0 0 0 0. Or the 0 3x2 matrix is like 0 0 0 0 0 0. So in general, like the 0 n by n matrix, right? It's like a matrix where every entry is 0. Okay. Why? So usually, you know, it's like sometimes you specify the size of this matrix, but since it's kind of, you know, sometimes you just call it 0 because from the context you will kind of realize of which size you're referring to. So sometimes, like, you know, it's kind of like sometimes you would just write this as 0 as an, you know, sometimes you will write this as 0 or 0 matrix, and then the context will specify which size you're referring to. Will specify the size. Now, why is it called? I mean, the size of it. What are the two properties like that you remember from the number 0? Well, one property of the number 0 was that if you add 0 to anything, you get that number back, right? So here, this is kind of true. If you add A to the 0 matrix, right? It doesn't matter what A is, you still get the original matrix A back. So that makes sense because you're just adding each entry with 0, right? So it doesn't affect the entries of A. And the other one is kind of like, you know, if you multiply A times a 0 matrix, again, assuming that the sizes are chosen correctly, right? If you get A times the 0 matrix, well, that actually gives you the 0 matrix, right? So because like everything will die when you start doing the multiplication, and that will also be like the 0 matrix times A. Is that making sense? So like, I mean, the 0 matrix is really like the number 0. It is the closest thing to the number 0 that you could expect for in matrices. Okay. Now that there is a thing that does change, and so that's why I started talking about this first, because if you remember with numbers, when you had numbers, so with numbers, if you had that the product of two numbers equals 0, the number 0, what had to happen with those two numbers? At least one of them had to be 0, right? So at least one of them had to be 0. The number 0. But with matrices, that does not happen. But with matrices, so that's kind of what I wanted to write here. But with matrices, you can have two matrices A, B, for which A times B is a 0 matrix, but neither A nor B are the 0 matrix. Okay, well, let me copy. No, well, it is, sorry, just to answer that question first, it is of the size that's needed to make the multiplication make sense. So for example, like if A had been 2 by 3, right? Then the 0 matrix would need to be 3 times something, and this something can be whatever you want. So, but because that already makes the multiplication well defined, right? So whatever number you put here, it doesn't matter. It will still get like give you like a 0 matrix of like the like a corresponding size. Is that making sense? So like I'm just saying like just choose like just choose a size for the 0 matrix that will make this multiplication have like the right size, and then it will always give you the relative, like the corresponding. Right. It can be any 0 matrix that works with A. That's what that's why I'm just writing it as 0 matrix, so that it kind of adjusts itself to the context. Yeah, but it's kind of it wouldn't change like because you just have so many bunch of zeros, so any dot product will be 0. You know what I mean? But yeah, it doesn't have to be like a specific size. It only has to be of a type for which the multiplication makes sense, and then you're good to go. Is that making sense? Okay, so let me give you an example of this. So imagine that I had taken A to be 1, 1, 1, 1, and B to be. So here's an example of this property of this thing. 1, 1, minus 1, minus 1. So what if you do AB? Notice that okay, neither of them is a zero matrix. In fact, none of them have even like a single zero in any of their entries, right? None of them have like even a single zero. But if you do their multiplication, you get 1, 1, 1, 1 times 1 minus 1, 1 minus 1. I mean, again, hopefully over time you will get used to this, but when you do this dot, like the dot product of this with this is like 1 minus 1, so this will give you 0. When you do the dot product of this with this, it's 1 minus 1, so it gives you 0. And when you do the dot product of this with this, it gives you 1 minus 1, so it gives you 0. And when you do the dot product of this with this, you get 1 minus 1, so it gives you 0. Is that convinced? So is that okay? Is that calculation okay? So everyone gave you a 0, entry 0. So you did get the zero matrix 2 by 2. Is that okay? So this is an example where you have two non-zero matrices in like an extreme case, because neither of them have even like a single entry equal to 0, but yet when you multiply them, you can get the zero matrix. So you have to be, this just means that you have to be careful with matrices, because sometimes like some of the assumptions or some of the facts that you know work for numbers no longer work for matrices. Is that okay? In fact, it's actually like a little bit worse than that, because like if you do it in the opposite order, then you get something completely non-zero. So what if you do B times A? So if you do B times A, you get 1, 1 minus 1 minus 1 times A, which is 1, 1, 1, 1. Okay, let me bring some coffee. When I get back, someone maybe can tell me what the entries are. Yes, I agree with what you're writing. So there should be 2 is the first one, 2, 2, 2. Okay, now let me just check. Yeah, it's minus 2 and minus 2, right? Is that what you, yes, I agree. Yeah, good. So like this is a good example, because it's kind of like if you do it in one way, you get a bunch of zeros, the multiplication. If you multiply the other way, you get something where, again, every single entry is not even 0. So it just shows you how careful you have to be when you do multiplications, because you cannot just assume like things that would seem very natural. Like, kind of, unless you're given like unless you were told that this property works, you probably shouldn't assume that the property works. Okay. Is that making sense? So this is the next one is of a thing that doesn't work, is kind of similar, in the sense that there's no cancellation property in general. So in general, there's no cancellation property. And let me tell you what I mean by that. Cancellation property. So again, like if you remember with numbers, if you had that AB equals, let's see, or let me, yeah, A equals AC and A is non-zero, you would say that then B equals C, right? That's what you would do with numbers. What I'm saying is that the same will not happen in general for matrices. So for matrices, we can have that AB equals AC, where A is not the zero matrix, and yet B is different from C. Okay. So let me give you an example for that. So you could take, for example, this should work. You could take A to be 1, 1, 1, 1, B to be 1, 1, 0, 0, and C to be 0, 0, 1, 1. And so you could AB, if you do it, AB is going to be 1, 1, 1, 1, 1, 0, 0, 0. And if I did this correctly, you should get 1, 1, 1, 1. And if you do AC, you get a 1, 1, 1, 1 times C, which is 0, 0, 1, 1. And again, this should also be 1, 1, 1, 1. Okay. So you see, like they have the same first factor. The same first factor is the same. The second factors are different, but still you can still get to the same product. Is that making sense? So I mean, again, we'll discuss, like, there are cases where this does work, where you can cancel. Like it's like what happened, like with numbers. The reason why you could cancel is because you could, like, you can think about it. You could multiply both sides by 1 over A, right? You could, like, invert a number, like take the reciprocal of a number. The thing with matrices is that you cannot always take the inverse or the reciprocal of a matrix. So we'll talk about those cases when that happens next week probably, and those are the cases when the matrix has an inverse. So whenever the matrix, if A had an inverse, then you can really just cancel it on both sides. But if the matrix has no inverse, then you cannot do that. So, like, the example that I'm giving you here is like an example where the matrix does not have an inverse. But again, that shouldn't mean too much right now, because I still haven't said what I mean by inverse. But I'm just explaining that that's what's going on. This matrix doesn't have, like, a reciprocal. So, like, the issue here is that what went wrong is that 1 over A does not exist. I mean, and also one, you have to be careful. Like, let me just write it as A inverse. Does not exist here for this A, but I still have to explain what that means. Yeah, if I have time, I'll may get to it today, but if not, I mean, right. Only if A has which we will be called an inverse, it can be canceled. Yeah. So it is not enough to have A on both sides. You have to have an A on both sides that have, like, what we'll call an inverse. Yeah. And then you can cancel. Yeah. Oh, good. There's a group me. You should join it probably. To keep in. Well, the idea of inverse is that yeah, you get like an well, I'll explain what the inverse is, but yeah, you would get like the inverse is that, like, A times its inverse gives you the identity. Although I still haven't said what I mean by the identity matrix. I have to. That actually could be the same. That could be like a good excuse to talk about the identity matrix. So We can return to this example once I have talked about the inverse and the identity. But yeah, well, that does. We need a couple more days of class before I can tell you that. It is a couple of a secret for now. Yes, I still cannot give you an example because we don't have enough theory for how to do that.
So I don't need to I don't need to know how to do the inverse for now, right?
Yeah, you don't need to. I still even haven't really said what an inverse is. I'm just saying that there's will be this thing called an inverse, and that's what's going on. But yeah, I still haven't said anything about how to do this inverse thing. So we'll do it next week for sure, but not today because we still need a little bit more of a theory before we can get there. No, actually, you can do it before the determinant. We will do it before the determinant. So yeah. The determinant will be useful for that, but it's not necessary. Yeah. Yeah. Well, let's talk about at least the identity matrix since everyone has brought it up. Some of you brought it up on the chat. So the identity matrix, this only is defined for matrices of with the same number of rows and columns. So this is called the identity matrix I times n, in times n. So that means like it's going to be a matrix with ones along the diagonal and zeros everywhere else. With ones along the main diagonal. I'll write them out. Diagonal and zeros everywhere else. So just for example, what is the identity matrix of size 2 by 2? It is 1, 0, 0, 1. So you see, like this is what usually is called the main diagonal. So you put ones there and everywhere else you put zeros. So what's the identity matrix of size 3 by 3? You have 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. And just to put one more, because hopefully this is kind of like the pattern is clear. What is identity of size 4 by 4? You put 1, 1, 1, 1, and then 0, 0, 0, 0, 0, 0, 0, 0. Oops, like yeah. This is fine. It just looks a little bit off. Let me move this one around so that it looks a little bit nice. Okay. So like, writing these matrices, I mean, the thing is like, if the matrix has different size, if it's like 2 by 3, like if you have like something that's 2 by 3, it's not clear, like, where you would put the one. So it's not, that's like, you kind of need it, like, there's not like an obvious diagonal if the matrix is not a square matrix. Yeah, so that's why it has to be a square, because only when it's a square, there's like a clear diagonal where you can put place the ones. So yeah, it has to be, so number of rows has to be equal to number of columns for this matrix. That's why I wrote here n by n, because we do require those two numbers to be the same. So it's always a square matrix. But the idea is that it is the closest thing to the number 1. So in what sense? That if you had a matrix, let's say that is n by n, right? If you had like an n by n matrix and you multiply it by the identity matrix, right? You have to put like this matrix of size n so that these two numbers agree, right? Then this will give you the matrix A again. So it's kind of when you multiply a number by 1, you get that number back. The thing that the identity matrix does is essentially the same. When you multiply a matrix by the identity matrix, you get that matrix back. So it kind of leaves the matrices on, does nothing to the matrices when you multiply them. And likewise, if you had, if you can also put it on the other side. It's just that here you have to change the size of the identity matrix you're using. Because again, like when you do the matrix multiplication, these two numbers need to agree. So now you would need to change the size. So you would put here identity, but you will still get the matrix A. So it kind of behaves like the number 1 does for multiplication. So it behaves in the same way. As a number 1. Is that making sense?
Professor, I'm still confused why like I times A equal to A, like the formulas.
Oh, you mean this one?
Yeah.
Well, you can do it like with an example. Like what I'm saying is like, for example, let's say A is like, let's do something like this. This is like 2 by 3, right?
Yes.
So if you wanted to multiply this by a matrix, by an identity matrix, you would have to multiply by 1 0 0 0 1 0 1 0 0 0 1. Like that's the only one that for which this would make sense, like the multiplication, right? And so that what I'm saying is that just if you start doing the products, if you start just doing the dot products, the thing is like since it only has one in one of the entries and zeros elsewhere, like it kind of only multiplies one entry of the matrix by 1, and so that's why it preserves the, it kind of does nothing to the entry. So that's why you get 1 2 3 0 minus 1 2. Is that making sense?
Yeah.
And what I'm saying is that you could also have put the identity matrix on the other side, but now it has to be 2 by 2 because that's the only way to make it match in terms of sizes. Because again, like the numbers, like the numbers have to match. But again, if you do this multiplication, since it has a 1 and zeros elsewhere, it kind of just like records the entry of the matrix in a sense. So it's 1 2 3 0 minus 1 2. Is that making sense?
Yeah, gotcha.
So it's really like the number 1. It behaves like multiplying by the number 1. So in general, it's not doesn't cause too much confusion. But yeah. Okay. Now here's another question about the identity matrix. Here's another property of the identity matrix. If you had the identity matrix, like, I mean, we can do it. And you had a vector, right? What would be what would be the identity matrix times a vector? So like, again, you can do it if you want concretely for like a specific case. right? So what's the answer in this case? Right, it does literally nothing to the vector. It's kind of, because a vector, again, as I said, is kind of like a special case of a matrix if you want to think about it in that way. But yeah, so if you take the identity matrix times a vector, you just get that vector back. So that's also why the name identity gets used for this matrix, because it is like, if you thought about it, if you like those machine diagrams from before that we had talked about for a while, like you can think that you have like a vector, right? And if you have the identity matrix representing that machine, the machine, the identity matrix machine is like the do nothing machine. It just returns the same output that you fed to it. So it does nothing to it. So the identity matrix really leaves matrices untouched and vectors untouched. It really affects nothing when it comes to multiplication. So it leaves everything the same. Okay. Is that okay? Are there any questions up to this point? So before I keep talking about this, at least let me mention two properties that do work. So I have been giving you like a list of things that do not work. So let me give you two things that actually do work. So two things that do work. The first one is that the product is still distributive. So the matrix multiplication product is still distributive. So that's kind of useful to know. And so by that, I mean that if you have like A times B plus C, again, when I write this, like I'm implicitly assuming that like the multiplication makes sense in terms of sizes, right? So that this would have the right size. But what I'm saying is that if you had like something like A times B plus C, that is the same as A times B plus A times C, okay? And likewise, if you had B plus C times A, that's the same as B times A plus C times A. But just keep an eye that when I write it this way, I'm not changing the order of the factors, right? So if I had A on the left side, right? If I had A on the left side here, it appears on the left side when I distribute. And if I had A on the right side, it appears on the right side also when I distribute. Okay. Is that making sense? So if you have like if you have like like if you have like parentheses, you can still distribute the multiplication, but you just have to keep in check that you are not changing the order of the factors. Okay. Is that making sense? Well, I'm about to do an example, but is that making sense? Is the property making sense? Yeah, with numbers, that's fine. Yes. We will do some examples later about matrix equations, but yeah, you could multiply, you can divide by scalars. Yes. Yes. That is fine because it's a number. Yeah. So like, let me give you an example of this. So anyone remembers, so here's like for numbers, what was, anyone remembers what A minus B times A plus B is or was? What was this equal to? Well, that not quite that one. This is because this is the difference of square formula. So it's not this way. It's like, well, no, it's a square minus b square. Yeah. What the one you're thinking about is this one where it's like a squared plus minus 2ab plus b squared. But that's like these two are you know, they're slightly different. You know, they're not the same because like here, like here like each factor has a different sign. Like one is like a difference and one is with a plus, and here like each factor is kind of repeated twice with the same sign. Okay. But now let's try to find the analog of this for matrices. So what's the analog of this for matrices? And again, like for this, so let's try to find like the version of these identities for matrices. So what's the version for matrices? I don't know if you remember yesterday, if you want to talk about the square of a matrix, you have to have like the matrix to be a square size matrix. So here, let's take A and B square matrices of the same size. So what would be A minus B times A plus B in the world of matrices? So here's where you have to be careful. What I want to do is distribute, but when I distribute, I have to be careful with the order. So I'm going to distribute like this. I'm going to distribute this one here and this one here. So that would give me A times A plus A times B. Okay. And I can also distribute here. So I can get this one with this one and this one with this one. But now, because of what I was saying about the order, this is minus B times A minus B times B. Is that making sense? So what do we end up with? We end up with A squared, right? You can write it this way. You can write it as, let's write it with, so this is A squared, like the first one is A squared plus AB minus BA minus B squared. So you see, like the thing with matrices, if, you know, with numbers, we never see this factor, right? With numbers, this always is 0 because with numbers, it doesn't matter the order in which you do the multiplication, right? But with matrices, like in principle, there could be matrices where this is the 0 matrix, but there could be matrices where it is not. So you cannot, like that's the best you can, you know, you can write this formula as, because you cannot necessarily say that this is a 0 matrix. You see, so this is actually the identity for matrices. Like it's just like a little bit. You can write it if you want. You can put it like a squared minus b squared, which is what you would get like from like the same as numbers, plus this term which may or may not be zero. Is that making sense? So it is kind of like the difference of square formula for the matrix version. But it cannot be further simplified unless you know more about the matrices. That's what I'm trying to say. This may or may not be the zero matrix. Is that making sense? It depends on A and B. And the same happens with the other ones. So for example, if you wanted to do like a plus b squared, right? Let's say I wanted to do a plus b squared. What does that mean? It means a plus b times a plus b. Okay, and I'm going to distribute like as before. So this gives me a squared plus ab. And then when you distribute here, you get ba times b squared. So again, in the world of numbers, you can just replace this with 2ab. And that's usually how you would see the formula. But it's in the world of matrices, like these two quantities could be different. So you cannot further simplify this anymore. So you can't simplify this further. Unless you know more about A and B. Is that making sense? No, well, no, if AB equals BA, it's not, no, it's just that, I mean, that's the same with, like, if AB equals BA, right, for example, I can write this down. If AB equals BA, but this is a big if, then this becomes A squared plus 2AB plus B squared, right? But I mean, that still doesn't guarantee that AB will equal A squared. You know what I mean? But that's the same that happens with numbers. You can say that, but only, again, you can say that's true, but only if this happens. Well, yeah, if you're talking about matrices, right? That, yeah. So this would be A plus B squared. Yes. But again, under this big if. Is that okay? So I'm just saying that the usual identity is not true unless, oops, the usual identity is not true unless you know that you can switch the order of the multiplication. Oops. If not, you have to stick with this one. Okay, and then the other property that does work, so the distributive property does work, which is what I was saying here. You just have to be careful about not changing the order of the factors. The other property that does work is called the associative property. So what does I mean by that? I mean that if you had three matrices, right? If you had three matrices, like, and you want to multiply A and B together, and then multiply that by C, that's the same as multiplying A with the result of B and C. So I mean, this kind of hard to say it works. What I'm saying is that you can move the parentheses around when you're doing the matrix multiplication. So what this is saying is that you can move. So here, like, it's not that I'm choosing to, I mean, notice that I'm still writing A, B, and C in the same order. It's just that to do the product, you can choose to do like first, like group them in this way or group them in this way, basically. So, you know, kind of like what I'm trying to say is like, if you, just to make an example, yeah, let's see. If you had like, you know, 1, 1, 1, 1, 1, 0, 0, and then, I don't know, let's do, 1, 1, 1, 0. Okay, what I'm saying is that if you had these three matrices and you wanted to multiply them, you could choose first to multiply these two. Okay, so when you multiply these two, if you do the product, that's the same as, I think I had done it before, that's why I chose this example. Yeah, you get 1, 1. Maybe I'll put like an example where like, just to do something different. Sorry about that. Okay. Okay. Yeah. So if you multiply these two first together, you get 1, 1, and then you get 0, 0. And what you get, you can multiply against 1, 1, 1, 0. And that gives you what? It gives you 2, 1, 0, 0. Okay, so that's like the first thing you could do. Or you could have taken these three same matrices and you decide to do this product first. So you're going to leave the first one alone. And what do you get when you do this product first? You get 2, 1, 0, 0. And this gives you 2, 1, 0, 0. Okay, so I'm saying that, you know, when you have a matrix of, when you have a matrix multiplication, a matrix product involving 3 or more matrices, you can decide to group them together and do the products individually in the groupings, as long as you don't change the order in which the matrices appear. So I'm always preserve, you know, this one was the third one, so it always was kept last. I didn't move it around. And this one was the first one, so it was always kept first. So I didn't move them around. So as long as you don't move them around, you can do the multiplication in different, you can do the groupings for the multiplications in different ways. Is that making sense? Okay. So again, like the associative property in practice just means like you can move the parentheses, and you can put the parentheses where you want them. Okay. And okay, just in the in the remaining minutes, let me tell you a little bit about the inverse of a matrix. So let's talk a bit about the inverse of a matrix. Before doing the quiz. So I will just tell you a very brief introduction to this because it will require a lot more time to discuss. But so what is a is going, okay, let me start first with numbers. It's better to start with numbers first. So let's talk about numbers. If you had a number, right, what was A inverse? Oh, you could say that is 1 over A, right? But that's kind of redundant. I mean, like this, like the difference between this and this is just like a notational difference, right? What was the key property of A inverse? The key property of A inverse, right? What was the key property of the reciprocal of the number? Was that if you do A times A inverse, what would you get? What is A times A inverse for numbers? It's just 1, right? So the key property of the reciprocal is that it just gives you 1 when you multiply a number with its reciprocal, right? And that's the same as A inverse A because, for numbers, it doesn't matter. It doesn't matter in which order you put them, right? So what makes the most sense when you want to talk about do this for matrices is exactly to use the same definition with the corresponding, like, with a slight modification. So here, if A is going to be A, now it's going to be a matrix, right? Well, actually, we'll do it as a square matrix. We will say that A has an inverse if we can find a matrix A, a matrix which we will call A inverse with the property that A times A inverse equals the identity equals A inverse A. Okay. Is that okay? Is that making sense? So like what I'm saying is that if you, the important thing is emphasis in the phrase if we can find. So what I'm trying to say here is like, if you manage to find a matrix that when you multiply it with A, you get the identity, then you have succeeded in finding its an inverse for it. Okay.
Professor, I have a quick question. How
Yes.
did you get like a times a negative 1 power equal to 1? How did you get this?
No, it's like the definition. So it's like kind of like, you know, how would you get this? Like, I mean, you know, for numbers, like, how would you do this for numbers? Well, I mean, the way in which like you end up doing this is like you would say, well, you add the exponents if you want, right?
Yeah.
So you get a to the 0, which is just 1, right?
Yeah.
What I'm saying is that for matrices, we're just saying if you can find a matrix which you're calling A inverse, I mean, that's like the name that you're giving to this matrix. If you can find a matrix that has this property, the like you can call it like something else before that. So you can call it like B if you prefer.
Mm.
Like, oh, let me like what I'm trying to say is that so like what I'm saying is that so I'm saying like if you can find a matrix, B, satisfying A times B equals the identity, right? Equals B times A, then it makes sense to call that matrix the inverse of A. You see? Then it makes sense to think of B, to call B A inverse, since that's what would happen in the case of numbers, you see? And that's what's happened, since that is what happens.
I mean, like, can you give an example?
Yeah, I'm just checking first if like the notation is clear. I don't know, like, is this making sense? Like, what I'm just saying that with numbers, like the inverse has like the property that the multiplication gave you 1, right? What I'm trying to say here is like with matrices, you're trying to find the same condition. So the same condition should be finding a matrix whose, when you do the product, you get the identity. You see,
So
it is,
it's the identity, like it's the identifying matrix.
Right, like yes, the one that was like 1 0 0 1 or something like that.
Or
Yeah,
have to be the identifying matrix, or
yes, it has to be the identity matrix. So let's try to it is actually like this is let me do it this way. So it's more clear, like it will be more clear this way. Okay, this is one of I think it was one of the problems I had given you before. This will clarify things, I think. So you had a vector, right? If you had a vector, I had given you at the beginning of the course, I think like the rotation matrix, right? Where you rotated this by an angle theta, right? And you got like the rotated vector, right? So this was like the rotation matrix. Rotation. Which was okay. So for example, like okay, So if you had a vector and you wanted to rotate it, you would use this matrix, right? Now imagine that I asked you, well, how can you undo the rotation, right? So what if you wanted to take, if I take this vector, right? What should I do to rotate? How could I rotate it to get to the original vector v? What would you do? How could you rotate it to get to where you started? What would you rotate? Right. So there are two ways to think about it. Like, just to make this more concrete, right? Imagine that this had been 30 degrees, right? So by what amount do you have to rotate the blue vector to get back to the green vector? Well, you could say that it should be, you could say that it should be 330 degrees, right? Or another way to say it is that you can just rotate in the opposite order. You know, this rotation was clockwise, counterclockwise, so you could just rotate clockwise. So you could say, you could consider rotating by minus theta. So if you rotate by minus theta, you would get here cosine of minus theta minus sine of minus theta, sine of minus theta, cosine of minus theta, right? But what, anyone remembers what's the cosine of minus theta? What's the cosine of minus theta? It's cosine of theta, good. So there's a cosine of theta here. What's the sine of minus theta? It's minus the sine of theta. If you
Negative sine theta.
yes, and then here, like, you can do the same, but there was a minus already. So like, I'm going to put just sine of theta, right? Because the minuses cancel out when you take this one outside. So my claim, okay, so what am I trying to say? My claim, like, here's what I'm trying to say. So the claim that I'm making is that the inverse of the rotation matrix, right? So I'm saying that the inverse of this matrix is going to be the inverse of the matrix that rotates by counterclockwise by theta is going to be the matrix that rotated clockwise by theta. So it's going to be this matrix that we just found. Okay. So my claim is that finding the inverse is kind of finding like the matrix that undoes what the matrix, like the original matrix was doing. So because the rotation matrix was rotating theta counterclockwise, the operation that undoes that is rotating clockwise by the same amount, okay? But again, when you claim that you have found an inverse, what that means is that if you multiply these two, you should get the identity. Okay, so how do you check that this is correct? So how to check this? The idea is to multiply the two matrices to see whether you get the identity matrix. Multiply them out to see if you get the identity. So what happens when you do cosine of theta minus sine of theta, cosine of theta, times what's the black matrix is cosine of theta, sine of theta, minus sine of theta, cosine of theta. What do we get when well, no, we still cannot that does require a lot like that would take more time to like we need to talk about other things before like talking about the general case of how to find it. Oh no, there are definitely four formulas for the inverse. It's just that it does, like, it wouldn't make a lot of sense right now if I tried to give you like a general formula for how to do it. We need to talk a little bit more about. I'm trying to like do it in an example where like we kind of expect what the answer should be. But yeah, like the general formula is kind of complicated. So.
Oh, Professor, quick question.
Mhm.
That is above rotation, that with the theta or negative theta? I mean,
So the first
theta.
the first one is for theta, right? With
Yeah.
theta, and the second is with negative theta.
Okay. Oh,
Yeah.
gotcha.
So what I'm saying is that if you do these multiplications, like you get you get cosine of theta, sine of theta, minus like sine of theta, cosine of theta, and then you get sine of theta, cosine of theta, minus cosine of theta, sine of theta, and then you get at the bottom, you get cosine, you get sine square of theta plus cosine square of theta. Is that making sense? So that's what you get when you do the multiplication of these two matrices. But what happens here? That doesn't look like the identity. Well, okay. Let's see. Like these two things cancel, right? Because they're exactly, I mean, these are exactly the same term and these are exactly the same term. So these cancel out. So that's why you get a 0 and 0 here. And what's cosine square plus sine square? Cosine square plus sine square, you should remember that's just 1. So that's so you do get the identity for it. Does that make sense? So the inverse of like the rotation by theta degrees is rotating by minus theta. Let's do another example. We still have some time. So here's another example. Do you remember, like I had given you, when you had like a vector, we had found the mirror vector, right? I don't know if you remember this one. Like there was this matrix that took care of taking this vector to its mirror, right? What was that matrix? Anyone remembers the answers? Good. It was 1, 0, 0, -1. Okay. So now imagine that I tell you, okay, so if you want to take this vector to its mirror, you use this matrix, right? What would you do if I wanted to take the mirror matrix, sorry, the mirror vector to itself? How could you undo the effect of the reflection? What would you do? What would you do if you wanted to go backwards? Well, now this is not a rotation. There's not like an angle. I mean, it is. I mean, it's right. Exactly. Okay. So if to find this the mirror image, I use this matrix, right? If you reflect it again, you should get back to where you started, right? So it should be. What this is saying is that the mirror matrix should be its own inverse because it has the effect, it cancels itself. So my claim is that the inverse, my claim is that the inverse of M is going to be itself. So it's going to be 1, 0, 0, -1, because if you reflect an object twice, you get to where you started. Okay, so let's check that out. What happens when you do 1, 0, 0, -1 times 1, 0, 0, -1? You get 1, you get 0, you get 0, and then you get -1 squared. So you get 1, 0, 0, 1. So this is an example where the matrix is its own inverse, and that can happen. Basically, if you do these things again. Okay. So again, like I'm not. Oh, sorry, you were going to ask something.
Yeah. So right here, M is equal to the M -1 power.
Yes, it's its own. Correct. Yes.
All the
It
time.
is the same. No, only for this one. Not only for this one, but only in certain cases, not all the time. I mean, is that M had like a specific meaning in this case, right? M was this specific matrix. I'm just saying that for this matrix, it is its M inverse as well. So it just happens to agree.
Okay, because I know we're gonna have the condition is when we are in the identify metric.
In the identity, yes. You get here the identity matrix. But I'm just saying that like for example, in this case, the inverse, in the case of the rotation, the inverse was rotating by -θ degrees. In the case of the mirror, the inverse is just like the same matrix. But yeah, like this is kind of to give you like a sense that like the answer can actually depend a lot on what the matrix is. That's what I'm trying to say.
I just confused like what condition are we in, then we can just like use AB equals.
No, I will write a formula for next week. I'll give you like a condition you have to check for like an inverse to exist. I'm just doing it like in specific examples, because in specific examples you can understand more concretely what's going on. And the idea is that you should think of the inverse as a matrix that undoes what the original matrix was doing. So here's another example before doing the quiz. So think about this matrix. This is an easy one. Okay. So I think this one will help. So what does this matrix do? If it has a vector xy, what this matrix will do is produce a vector whose entries are 2x and 3y, right? So it's a vector that that doubles the first vector, the entry of the first vector, and triples the second entry of the vector, right? So this matrix multiplies by 2 the first entry and multiplies by 3 the second entry, right? So the question would be, what operation, right? What operation would cancel out this effect? right? So if you had this vector, how could you bring it back to the original vector? What would you try to do? How would be a way to cancel out the effect that this did? How could you get back to X, Y? If you have 2X and 3Y, how can you get back to X comma Y? I guess that's the question that I'm asking. Yeah, you should divide by 2 the first entry, and then you should divide by 3 the second entry. That should cancel out the effect. So that suggests that the inverse of this matrix should be 1/2, 0, and 1/3. And that does happen if you do 2, 0, 0, 3 times 1/2, 0, 0, 1/3. If you do this multiplication, you will get 1, 0, 0, 1. No, it would be open-ended. Yeah, exactly. That's the point. The inverse is a matrix that reverses the effect of the original matrix. It's like a cancellation matrix. It's undoes the process. Yeah, that's what I was trying to explain with these examples. So you had a vector, you did something to that vector, you want to reverse the damage. For that, you use the inverse. So it's kind of like, if you prefer like the analogy with pictures, like, it's kind of like you have a photo, the inverse is kind of like applying a filter to the photography. And then the inverse is kind of like removing the filter. You know what I mean? So it's kind of like the point of the inverse is to remove the effect of the matrix, of the original matrix. It cancels out the effect of the matrix. The thing is like, again, there's like a formula for doing that, but I was just doing some examples for you to understand like that. That's kind of what's going on. The formula, I'll give it to you next week, but it would take a little bit of time to get there, like to get to the general formula. There is like a general formula for the inverse. It's just that it's still, we need to work it out more carefully. But yeah, in terms of like the vectors, what you should think of the inverse is like undoing the effect of the multiplication. Is that making sense? Okay, so again, we'll keep talking, like the inverse is an important concept. So we'll keep talking about the inverse later on. But I just like wanted to introduce it for now because again, we have to discuss it more next week. So next week, we'll keep talking about the inverse, but it's just kind of like a good thing to keep in mind for other things that I was saying. So let's see. So let me see if I can show you the Firefox. Yeah, so let's see. I can show you this. So I think, okay, here's a quiz. Oh no, this is 10 a.m. So yeah, you should now be able to take the quiz. I think you have like 25 minutes to answer that. There are only 2 questions. Then once you answer them, just take a picture of your questions and upload them here on this assignment that's called upload quiz 1. But for that, you have 15 minutes, 15 additional minutes. So yeah, you don't, on the quiz itself, you don't have to enter anything, I think. It's only on the upload that you have to enter your, show me your solutions. So, but yeah, you do have to log out of Zoom because, oh, sorry, I have to make it visible. You have to log out of Zoom because it has to use responses. You should write no, you don't need to write the questions. You upload after you leave lockdown browser. You can, so take the quiz on lockdown, finish writing whatever you want to write, leave the quiz, and then take pictures and upload those to the upload quiz assignment. But only the solutions, because I know what the problems are. Well, try again. But you shouldn't open it right now because you have to take the quiz first. Yeah, you answer the questions during the quiz, and then after you exit the quiz, you just upload the solutions to the upload assignment. Well, it's the questions that are on the quiz. Like the quiz has like some specific questions. Yeah, based on those, yeah. Well, not 19 because I removed 19 from the quiz. Well, it's due like in what, like 30, 40 minutes. Class is over now. Yeah, you can leave at any point that you want now. Yeah. The class is concluded for today. Yeah. Okay, good. You too. Bye. Let's see. Maybe I need to fix this. Thanks. Thank you. You can now. This should be. Now it should be fine. Thanks. Yeah, I think I had not chosen. Yeah, no, good. Thank you. No, thanks for letting me know. You too.